Our guest today for the Rotary E-Club of the Greater San Fernando Valley is Emily Lakdawalla. She's Senior Editor and Planetary Evangelist for the Planetary Society, and we're here in Pasadena, California. Emily, thank you for being with us.
It's a pleasure to be here.
So, first question for you is, what brought you to this field of study with the planets? I understand you're a geologist by background.
That's right. I was always interested in science, but I hated specializing. So I kept on finding the track that would allow me to do the most different kinds of science. And in college, that led me to geology, where I also got to hike around outdoors and walk around on rocks and do art to draw these geologic maps and answer mysteries. And then when I thought about what I wanted to do for graduate school and realized that I could study geology on other planets, it was really a no-brainer. I had to go do that.
At some point, hopefully, you'll get to walk around on some of them in the rocks.
Honestly, I'm actually very happy with robots doing that for me, because robots can go to all kinds of uncomfortable places that I could never get to. So I'm happy to stay comfortably in my office on Earth and see through the eyes of robots across space.
And we're going to talk about some of those robots in a few minutes, because we learn a lot from them. They don't need a lot of atmosphere, which probably helps.
In fact, they mostly benefit by not having any atmosphere, so it just gets in the way.
So today, the Planetary Society, its mission is to encourage the exploration of our solar system and now beyond, as we're finding more. What drew you to the Planetary Society?
It was actually just a want ad at a time that I was looking for jobs that was just perfectly matched to my skills, because in addition to having trained as a geologist, I'd also been a middle school science teacher for a couple of years, and they needed help with an education project that was being funded by the Lego company to work on the Mars Exploration Rover mission, getting students involved in the mission. And so it combined everything I loved, excuse me, and I was just right place at the right time, and I've been there for 15 years now.
Yeah, so everything comes together at the right time. It's like when the planets line up for the mission launch.
That's right. When they get all lined up so you can do the gravity assist, it's just right place, right time.
So, as it happens, we're going to be showing this video during a month that Rotary International attaches a theme, and one of the themes is establishing new Rotary clubs. So we're looking for a few interesting places to set up a new Rotary club here and there, if it's possible. So I was thinking we would take a tour of the solar system and learn what's out there. That work for you?
Absolutely.
Okay, so let's get on the mental spaceship, not to steal too much from the cosmos concept. And let's circle in by the sun and get to the closest planet to the sun. That's Mercury.
That's Mercury.
What to you is the most interesting thing about Mercury?
Well, we just had a mission called Messenger that spent a couple of years mapping Mercury and finally crashed into it recently. And I think one of the coolest things about Mercury is literally a cool thing. It's at the poles, where there are these craters that, because they're holes in the ground at places where the sun is glancing across the surface, they're actually very cold. And so even though Mercury is close to the sun, a hot planet, there's these cold places that could trap ice. And so you could actually have a human settlement on Mercury if you were at one of those poles where there's lots of ice water around, where it's not so hot, if you wanted to. I wouldn't recommend it, but it's possible.
You'd need SPF 2 million, but you could be there.
Oh, no, because you'd be in the shade all the time.
All the
so
time,
you'd actually
okay.
you'd be in pretty good shape.
Is Mercury somehow locked into its orbit, so only one side faces the sun?
They used to think that for the longest time about Mercury, that it rotated once per orbit, just like the moon does at Earth. But it's more complicated than that. It actually rotates, let me see if I can get this correct, 3 times for each 2 times it goes around the sun, which means that the sun does very strange things. It doesn't just rise and set on a simple schedule. There are very long days, and the timekeeping on Mercury would be quite strange.
And don't even ask about daylight savings. Okay.
Yeah.
And you mentioned you threw something away in that conversation that I feel we should clarify. When you said that Messenger crashed into Mercury, that wasn't an accident.
No, it wasn't an accident. In fact, it's inevitable with a lot of space missions that once you run out of fuel, you will eventually crash. And it doesn't happen at every location. At Mercury, it happened in particular because Messenger had a very elliptical orbit, and the sun is so close by that its gravity tugs on that orbit in such a way that the orbit just eventually drags Messenger into Mercury. And so while they had fuel, they kept on pumping the orbit back up to stay up in the air or up above the surface. And then finally, they had no fuel left and they crashed. But they got so much out of that tiny mission. It was amazing.
So the crash was known that it was going to happen,
That's
but
right.
They didn't aim it specifically at a spot. They just knew that it was going to happen, and whatever happened
Well, they knew exactly where it was going to land because an elliptical orbit is very close to a planet at one specific point. So they knew the date and time of the crash, and they listened for the spacecraft, and it didn't talk to them after the time it was supposed to crash, so they know it's over.
Unless it was kidnapped by...
aliens, that's right.
Got it. Okay, just throwing that in. Okay, does Mercury have any sort of an atmosphere, any tenuous anything there?
It has something called an exosphere, which is made by the solar wind plowing into the surface and knocking ions off into space. But an exosphere is a region around a planet where there is so little atmosphere that the individual molecules never bump into each other. It might as well be a vacuum.
So let's cruise back away from the sun to a planet that has a slightly different type of atmosphere. Next one out is Venus. What is going on at Venus?
We actually don't know very well because of its atmosphere. Venus has a very thick atmosphere. It has a high level of sulfuric acid clouds that cover that atmosphere. The atmosphere is so thick that the pressure at the surface is like being a mile beneath the surface of the ocean, and it's hot enough to melt lead at the surface. So it's very hot. Electronics that we've developed on Earth just don't survive in that environment. And so we have sent, or the Russians sent spacecraft that worked on the surface for, a few minutes, maybe up to a half an hour, but sooner or later they overheated and died. And so one of my favorite ideas for future Venus exploration is to have a balloon that would float at a high enough altitude in the atmosphere that you'd be above the heat. It would be way cooler at a high altitude, but you'd still be below the cloud deck. So you'd be able to look down and see the surface and try to figure out things like, does Venus have active volcanoes? Which we don't know the answer to that question yet.
Can radar even penetrate any of this
yes.
well?
Yes, so we have mapped all of Venus with radar using first the Pioneer missions. The Russians did it with Venera orbiters, and then the Magellan mission, NASA Magellan mission mapped the entire planet. For a while, Venus was better mapped than Earth, at least at radar wavelengths. But it's really time to get some cameras down there so we can really see what's going on.
There's talk that at some point in its past, Venus might have been more like Earth. It's comparable in size, it's relatively comparable in distance from the sun, a lot closer, but comparable. Do you think that's a possibility in the distant past?
Oh, sure. And I think that really the question of why is Venus so different from Earth, why are the two planets so different from each other, is one of the fundamental questions driving planetary science. I mean, one of the main reasons we want to go to Venus is so that we can understand what it is about Venus, what it is about its history and its composition that have led it to be so different from Earth.
The phrase I've heard sometimes is runaway greenhouse effect.
Yeah, that's right. It's one of the... I heard it put to me this way, actually, that Venus and Earth, they both started out with roughly the same amount of carbon. On Earth, all that carbon is mostly trapped in rocks. It makes up calcite and marble and those limestone, those kinds of rocks. On Venus, basically, its entire complement of carbon is now in its atmosphere. And really, the only way for that to have happened is for some process to have acted over time to send all the carbon from the ground into space, and it's just in a runaway fashion that put all of the carbon into the atmosphere. Its carbon dioxide is trapping all the heat and making Venus the hellish place that it is today.
So the heat from the sun gets in, but it can't radiate back out.
The radiation from the sun gets in as light, and then it gets absorbed and re-radiated as infrared, which gets trapped. The light can penetrate, the infrared radiation cannot, and so it gets trapped inside, and that's how a greenhouse works on Earth. That's why they call it the greenhouse effect.
Okay, let's cruise past Earth now and go to the next one, which is starting to develop a traffic jam. Let's go to Mars, and setting aside what we'll talk about later, which is how to find Matt Damon and get him back from there. What is happening at Mars right now?
There are so many spacecraft up there. So there is Mars Odyssey, a NASA orbiter that's been there since 2001. Mars Express, which is an ESA orbiter since 2003.
European Space Agency.
European Space Agency, that's right. Mars Reconnaissance Orbiter is a NASA orbiter that's producing amazing photographs, these images from its high-rise camera. The pixels are 25 centimeters, a foot square. So you're basically talking about aerial photograph quality images of the surface of Mars from high-rise. That came in 2005. There are two other orbiters. The Indian Space Research Organization's Mars Orbiter mission, also known as MOM, has been in orbit for a couple of years. And then there is MAVEN, which is a NASA mission focused on the upper atmosphere. Then if we go down to the surface, there are 2 active rovers. There's Opportunity, which is the one surviving rover from the Mars Exploration Rover mission, and Curiosity, which is the gigantic nuclear-powered rover that I'm currently writing a book about.
When is that book coming? Because I've been sitting reloading Amazon over and over.
Yeah, hopefully next year.
Okay, that's good. We're looking forward to that. And we have a mutual contact through Rotary, who you get to talk to a lot, who's the project scientist for Curiosity, who was a guest speaker at one of our Rotary youth events, Ashwin Basavada.
Yeah, Ashwin is the greatest guy. He's really told me so much about the mission. He was there practically from its inception. And the Curiosity rover is so enormous and complicated that I'm learning it's really impossible for any one person to know everything about the mission. But if there's anybody who knows the most about it, it's Ashwin.
Does he let you drive it?
Driving a rover is not as simple as just, steering a steering wheel. There's actually these meetings that are, you're driving a rover on Mars, you're discussing how to drive a rover on Mars. But the meetings are so long and exhausting because every single command that you're thinking about has to be checked and double-checked and triple-checked, because if you make a mistake that affects the health of the rover, that's it. You can't send AAA to go fix it, So you've got to make sure that you get it absolutely right, absolutely safe the first time, or the rover won't be around for the next day of operations.
So you're saying he doesn't let you drive it? Okay.
No.
Just establishing this. We'll send him a note. See what we can do. Okay, let's cruise. We could spend forever talking about Mars. Unfortunately, we can't today. So let's cruise out. The next big object, we have to get through some stuff first. There's this concept. I want to say thing, but it's a concept called the asteroid belt. And I'm sure that there are people who sort of have heard of it, who maybe have seen an episode of Star Trek Next Generation where Captain Picard has to navigate through one, and the rocks are tumbling off each other, and everything's all bumped up against each other. That's not so much our asteroid belt, is it?
No, although there are hundreds of thousands of objects that we've discovered in the asteroid belt, there's a lot of space in space. And so one of the things that we learned at the very beginning of our robotic exploration of space is that you can basically just fly through the asteroid belt blind and never crash into anything. There was some concern about that before we sent the Pioneers, but they did just fine. And it turns out that if you really do want to visit an asteroid up close on your way through the asteroid belt, you have to really plan pretty far ahead. But a couple of the spacecraft that have traversed the asteroid belt have done it on purpose. So like the Galileo mission to Jupiter traveled by a couple of asteroids called Gaspra and Ida on the way, but they had to plan ahead. They had to specifically change their course to pass by those asteroids and take pictures as they flew past.
But more recently, there's been a mission that has, actually, as I recall, it's a record setter. Not only did it visit an asteroid, but it's the first spacecraft successfully to orbit one, leave, and orbit another.
That's right. You're talking about NASA's Dawn mission, and the reason it was able to orbit Vesta and then depart Vesta and go into orbit at Ceres later is because it has a unique power source called ion engines. They require a lot less fuel. They work by accelerating xenon ions to very high speeds. They don't produce very much thrust. So instead of having, 30 minutes of explosive rocket power blasting out the back of your spacecraft and then coasting the rest of the way, which is the way most spacecraft work, an ion engine spacecraft has its engine on most of the time and slowly adjusts its orbit. So you don't shoot past an object, you just kind of slowly approach it. Every day you might check and it gets a tiny bit bigger in your forward view. And that's how things were like with Vesta and now Ceres. And Dawn is almost done with its mission at Ceres. They've decided to keep the spacecraft there until it runs out of fuel. Unlike Messenger at Mercury, Dawn will never crash into Ceres. It will probably be in orbit at Ceres forever.
Why will it not crash there?
Because Dawn's at a much higher orbit relative to the surface, and so there are no forces acting to change its orbit in such a way that it would crash into the surface. Unlike Messenger at the Sun, where the Sun is so close by and tugging on its orbit.
Ceres doesn't have enough gravity to haul it down?
Well, if something is spherical and something is in orbit around it, then the orbit would never change. And so it's not about whether it has more or less gravity. It has to do with whether there are forces caused by non-spherical things or other things flying past that act to change the orbit. So an example of a place where this does happen is, I'm going to preempt your suggestion, go to the next planet, which is Jupiter. Jupiter is a very large mass, but more importantly, it's not spherical. It spins pretty fast, and so it has a bulge at the middle. Earth has the same thing. Jupiter spins faster than Earth does, and it's a lot bigger. That it has a noticeably non-spherical shape, and that bulge exerts a force on orbits. And so the Juno mission, which is at orbit at Jupiter right now, has this orbit that is going to change over time into one that will crash into Jupiter.
And since we're there, let's go ahead and to stick with Jupiter, because there's some really exciting stuff happening literally right now.
Yeah, Juno is a mission that just entered orbit at Jupiter this summer. It's going to be operating there for a little bit more than a year. And it is, unlike previous missions to Jupiter, it's designed to try to study the deep interior of the planet. So it's going to use gravity information. It's going to look at radiation emanating from the deep interior. It's looking at the magnetic field to try to understand questions like, is there an Earth-sized terrestrial rocky core at the center of Jupiter? Is there anything in the center or not? We don't know. We have guesses about what its deep interior is made of, but we really don't know. And these kinds of physics-oriented missions will be able to help us understand what's going on in there.
Now, Jupiter is the first object we've come to that, unlike the asteroid area and the first four planets, those are basically rocky bodies.
That's right.
Now we're back out at what are called the gas giants. What is Jupiter mostly made of?
Jupiter is made of the same basic set of elements that the Sun is, in roughly the same proportions. So it's almost all hydrogen and helium, with a mix of other slightly heavier elements. And like I said, there may be a rocky planet at the very core of Jupiter, but really most of Jupiter is Sun-like.
And we're recording this on the 18th of August. Juno's going to start doing its first round of really interesting stuff. Was it the 24th?
The 27th of August is its first periapsis, the first closest approach on its elliptical orbit since it entered into orbit at Jupiter in the first place. And when it first arrived at Jupiter, they were very conservative with the spacecraft. They wanted to make sure they were taking no risk. All the science instruments were turned off. This time around, they don't have to do anything with the rockets, so they've got all the science instruments turned on. So the scientists have been waiting. They're very happy that they entered orbit successfully, but now is really when the moment comes that they'll see if their scientific experiments are going to work.
We're talking about Jupiter, and again, I wish we had more time than we have, but visiting Jupiter involves a couple of interesting side trips. Jupiter has a ridiculous number of moons, some of which are large enough to be really interesting.
Well, I think the planetary scientists would argue that all of them are really interesting.
Of course.
But yes, it does have 4 standout moons. Those are the Galilean satellites, Io, Europa, Ganymede, and Callisto in order from close to Jupiter to far from Jupiter. And 2 of them, Ganymede and Callisto, are larger than Mercury. I'm sorry, Ganymede is larger than Mercury. 2 of the rest are larger than our own moon. And so they're all very large spherical worlds. Ganymede would be unquestionably a planet if it were orbiting the sun on its own. It's really big and really diverse and fascinating. Unfortunately, Juno is not a mission that's going to tell us very much about any of these moons. The mission is designed to study the interior of Jupiter. It's got an orbit that is polar and won't ever get very close to any of the moons. So the best that we'll be able to do is get some really tiny pictures. There is some science they'll be able to do, but we need a future mission like the mission that ESA, the European Space Agency, has planned to orbit Ganymede in order to tell us more about these moons.
And there is, in theory, on the book somewhere out there, a mission planned, intended for Europa. What makes Europa worthy of its own mission?
So Europa is an icy satellite like Ganymede and Callisto. It's made of water ice-rich mantle over a rocky core. And we think that actually most of these large icy worlds in the solar system probably have at least a small liquid water layer inside them. And so we're sure that Ganymede also does, for instance, like Europa, and Callisto may as well. The thing that makes Europa unique is that its surface is geologically very young. So we know that it's geologically active probably today. And the other thing that we know is that it actually has a relatively small amount of water. And the reason that that's important is because its liquid ocean is probably directly in contact with hot volcanically active rock. And that is a wonderful location for really cool chemistry to happen. And so if you're interested in questions like, is there life elsewhere in the solar system? You want to look for places where there's a solvent, like water, where there is energy, like geologic activity, and where there is a source of the building blocks for life, chemistry, the place where chemistry can happen. So all of those things are satisfied at Europa. We have no idea if there actually is life there, but it's a really interesting place to go look.
If there is active current microbial life in the solar system other than Earth, that's one of the top candidates.
That's right.
And probably one of the very few at this point.
Possibly, although it kind of depends on how you define places where life might exist. But yes, it really hits all the high points. A couple of other places include Enceladus, one of the moons of Saturn, and also maybe underground on Mars. Mars could have had a biosphere more likely in its past. It's a little harder now because it's so cold and arid and oxidizing on the surface. But who knows, if life had started there, it could be deep underground and still surviving there now.
Speaking of Enceladus, let's cruise that way and get to Saturn, and we'll touch on Enceladus again in a second. What's the most interesting about Saturn, other than, at least my layperson's opinion, the single most amazing photographic mission Earth has ever launched? Yeah,
so Cassini is there right now. Cassini is really the last of NASA's great flagship orbiter missions. Hopefully Europa will be that kind of thing again, but Cassini is just enormous, amazing. It's been at Saturn since 2004. It's produced millions of amazing images and data on the planet, its storms, its atmosphere, its rings, how the rings change over time, all of its moons. And Saturn has a lot of moons. It has more round moons than Jupiter does, but they're mostly of a smaller size than Jupiter's moons. Saturn has one really big moon called Titan. It's the second largest moon in the solar system after Ganymede, but it looks like the largest because it has a huge, thick, puffy atmosphere. And so Cassini brought with it to Saturn this little lander called Huygens that was built by the Europeans. And it showed us that we landed on the surface of an outer solar system moon. I mean, that fact just continues to boggle my mind. We did it in 2005. And Titan is a place that has this thick atmosphere. It has methane clouds that rain methane down into rivers that flow across the surface and into ethane-rich lakes that have waves, and they evaporate sometimes and leave dry pans, and then there's thunderstorms. And all of these things happen on slightly longer timescales on Titan than they do on Earth, because Titan has a 16-day day, and also because it's so much colder there. You know, Titan, what we would think of as rocks are made of water ice because it's so cold that water behaves like rock does on Earth. And then all of the liquids there are these liquid hydrocarbons, methane, ethane, and higher, longer length hydrocarbon chains and gunk that rains down from the atmosphere. It's a fascinating place. But then there's all these smaller moons. There's Mimas, Enceladus, Tethys, Dione, Rhea, Hyperion, Iapetus, Phoebe, and then a bunch of even smaller ones that each one of them is a unique world that's been really fun to study and visit.
And I want to touch quickly on Enceladus, because there's one aspect of that mission that Cassini has been handling that knocks me out. Enceladus gave us a surprise, visually.
Yes, so Enceladus is a rather small moon. It's only 500 kilometers across. And spewing out of the south pole of this teeny tiny moon is a 500 kilometer high, so same size as the moon, plume of water vapor and particles, water ice frosty particles and other material that's all entrained in that vapor. And every time Cassini looks at it from the right direction, you see these plumes happening. They're a little hard to see from the front because it's a very thin plume. There's not much mass to it. But whenever Cassini gets behind Enceladus, so that you've got the sunlight shining through the plume to Cassini, it just lights up brilliantly, and it's the most amazing thing. It makes this enormous structure called the E-ring around Saturn. It's this blue kind of tenuous ring that goes all the way around the planet. And it makes a snow that actually falls down back on Enceladus as well as on other moons in the system. So it's this teeny tiny moon that we really don't understand why it's so geologically active, and it's affecting the entire rest of the system. And the one cool thing about the plume is that it has to come from a liquid water source beneath the surface that clearly contains other chemicals, so there's another interesting environment for possible life. And it's very helpfully spewing it out into space, so you don't have to land on Enceladus to study its ocean. All you have to do is fly through the plume. And Cassini's been doing that. It has an instrument called a mass spectrometer that it can use to study the composition of the plume. Unfortunately, Cassini's mass spectrometer only goes up to a pretty low mass, so we can't look for interesting things like organic molecules with it, just because the masses it can detect aren't big enough. So if we manage to ever send another mission to Saturn, definitely it's got to have a mass spec on it that's going to be able to look at the much bigger sized molecules that can tell us about interesting things like, even if there isn't life there, maybe there are the precursors to life. Maybe this is an environment where life could originate, that kind of thing.
Now, the farther out we get, the less we know, which is probably good because we're starting to run out of time.
That's okay.
But the next planets out, which are also gas giants, like in that sense, general category like Jupiter and Saturn, are Uranus and Neptune. We haven't done much with them yet. What's out there?
That's right. We flew past both of them in the 80s with the Voyager 2 mission. And they're two very similar worlds. Actually, scientists are beginning to classify them differently from Jupiter and Saturn. Instead of gas giants, they call them ice giants because they're not made of the same proportion of elements as the sun is. They're made a lot more of ices, and ices include water, but they also include things like methane, carbon monoxide, other relatively light on the periodic table, but still there are all these materials that are icy generally at those distances in the solar system. People have gotten more interested in Uranus and Neptune recently because most of the worlds that we've discovered in other solar systems, extrasolar planets, are similar in size to Uranus and Neptune. And we know that they're really different from the Earth-like planets, and they're really different from the gas giants. But apart from that, we don't know a whole lot about how they work. And so sending a mission to Uranus or Neptune would be a great way to help us understand what's going on in solar systems far beyond our solar system.
Where we're discovering that many, if not most, have planets.
In fact, I read one estimate that says there is probably, on average, one planet for every star in the galaxy. Some stars don't have any planets, and many have several. So on average, the number of planets in our galaxy is the same as the number of stars, which is just mind-boggling.
We do not have time to talk about the Drake equation, but I'm going to throw it onto the page and let everybody look at it later. I remember that from high school, grade school, I think. I first learned about that in a summer astronomy course at Caltech, of all things. I should have gone in that direction. I should have been a science nerd. Beyond Uranus and Neptune, there is still a ridiculous amount of stuff that we won't have a lot of time to talk about, although about 14 months ago, Pluto was a pixel. And then something happened, and now it's a world. What happened?
Yeah, New Horizons flew past it. So that was a mission that was designed to do the first reconnaissance of the first world that had been discovered in the Kuiper Belt. The timing of the mission was interesting because everybody, the first question they ask about Pluto is about its status as a planet. And the reason that I get frustrated about that question is because the reason that Pluto's status was changed was because we discovered so many other worlds. And the visit of New Horizons to Pluto has just piqued my interest in what all of these other worlds are like. They have wonderful names like Eris and Haumea and Quabar and Makimaki and Varuna and Ixion and Sedna. And many of them don't have names yet because we haven't tracked them long enough. But I think a lot of people think of the Kuiper Belt as another asteroid belt, and it's not that at all. The Kuiper Belt has a lot more mass. It has a lot more big round worlds. It's like an asteroid belt where throw out the asteroids and replace them with solar system moons. So think about all those round icy moons. Think about how different every moon of Jupiter is from each other. Think about how different every moon of Saturn is from each other. And then double that, because if there's one thing we learned from the flyby of Pluto, it's that one world had 7, 10 different kinds of surfaces. We know that the Kuiper Belt is filled with very colorful worlds, covered with different kinds of ices, methane, nitrogen, carbon monoxide. They have weather, they have atmospheres, they have clouds. It's all operating on a very long and slow timescale because it's so cold. But I can't wait for us to explore other worlds in the Kuiper Belt beyond Pluto.
Is that where most of the comets are or come in from when they get perturbed?
In fact, it's not. There's a whole nother region of the solar system called the Oort cloud that orbits about 1 light year away from the sun, so vastly farther than any spacecraft has ever traveled, 25% of the way to the nearest star. And that's where comets come from. It's very far away. We've never actually seen any objects in the Oort cloud. It's too far for us to detect those small things. We only theorize that it's there because of the orbits of comets. Have their long ends are all out there in this region of space that we theorize there must be this whole cloud of cometary material.
So realistically, we are nowhere near completing is a ridiculous word to use. We're not even making a dent yet in our exploration of the solar system.
I'm glad you brought that up, because at the Pluto flyby, there are a lot of NASA officials talking about how we'd completed the initial reconnaissance of the solar system. And it's so far from the truth, because there's so many other worlds we haven't seen. We haven't seen most of the rest of the asteroids. We haven't seen any of the rest of the Kuiper Belt objects. We haven't seen any of the Trojans, which are asteroids that orbit in these funny gravitational spots ahead and behind of Jupiter. There are hundreds of thousands of worlds to explore in the Kuiper Belt, and I think unless we start mass manufacturing robots in space that can manufacture more of each other to go explore all these things, we'll never see them all.
It's interesting. What I thought to myself was every time we think we've found every single object in the solar system and we're done, all we have to do is call up video from Chelyabinsk and see one that we didn't see coming that exploded over Chelyabinsk, Russia.
That's very true.
I'm sorry, it's Chelyabinsk. The Kings used to have a player from there, and I have to be sure I pronounce it right. So let's cruise all the way back in just before we run completely out of time. We've looked at all these other objects around us in the solar system, not counting the star. We've got all of these different bodies. There are rocks and gas and round things and not round things. Come all the way back to Earth. What are we learning about Earth from what we are finding out about all of these other worlds?
Well, a big part of the reason to study the rest of the solar system is to help us understand Earth. Earth is an incredibly complicated system. It's a rocky planet that has active geology, so it's changing itself from below. It has water and weather on its surface, so it's changing itself from above. It has life, which is dramatically affecting the chemistry. It changes the kinds of minerals that rocks form. And so having all of those things in one place makes it devilishly difficult to understand our own planet and to make predictions about the future. So one way for us to understand Earth is to go to places that are a little simpler. Like, for instance, Mars has a geologic history much like Earth. Its surface geology looks really similar to Earth's in many ways. It has only a small atmosphere, though. It doesn't have any water currently affecting its surface. So it's kind of like subtracting some of those forces and effects. If we can understand Mars, then we can take it back to Earth and build our models around it to help us understand it better. Venus, it's kind of similar. It might have active geology, we don't know yet. It's got this thick atmosphere. The cool thing about its thick atmosphere is that it's so thick that the top of it doesn't really feel the bottom. So you have an atmosphere on a terrestrial planet that is simpler. You don't have to worry about mountains and oceans and how that is affecting weather from the bottom up. You can understand the climate from the top down. And again, modeling Venus's climate has really helped climate scientists understand and predict how Earth's climate is going to work in the future. And that's of obvious importance for human life on this planet. So it's space exploration. Ultimately, it comes back to us no matter what.
All the time. The one other thing we've learned is that all things being equal, I think we're going to have to keep the Rotary clubs on this planet for
That's
now.
Probably true.
Probably a good idea. I wish we could do this for another hour, but unfortunately, you probably have things to do. Our members probably are not willing to do an hour-long program. So I will have to leave it with Emily Lakdawalla, Planetary Society. Thank you for this wonderful tour of the solar system. We'll stop by the gift shop and the snack bar on the way out. And thank you so much for your time.
You're welcome. You can read all about it at planetary.org/blog.